Alright, so this video is going to be on predicting the outcome of acid-base reactions. Again, abbreviating reactions, Rxns is a common thing. Alright, so HA plus B, a generic acid, HA, generic base, B with a lone pair. We've got the equilibrium arrow going to A minus and HB. Okay, so again, HA is the acid, B is the base, and then A minus is the conjugate base, and then HB is the conjugate acid. And again, with the notation that the acids are going to be blue and the bases are going to be red, I'm highlighting this hydrogen in blue, and then I will highlight the lone pairs on the base in red, indicating the lone pairs are going to be doing the attacking of the proton H, the blue H on the acid. Okay, and then once that the lone pair attacks the proton, remember the two electrons in that bond between H and A both go to A. That's what creates that lone pair in the products side with the negative charge. And then we get HB as our conjugate acid. So the equilibrium arrow is something that we need to be familiar with. This is one of many reaction arrows that we'll see. But since it's an equilibrium, that means it can go forward and backward. And we also, what we need to make note of is that the equilibrium favors the weakest acid and the weakest base. Okay, and so we went over what determines or what values can indicate whether or not we have a strong acid or base. And pKa was that useful tool. And so what we want to do is remember that lower pKa's are going to be strong acids. And stronger acids provide a weak conjugate base. Okay, so let's talk about some practice. We have a CC double bond, and that plus H minus, which is a hydride, goes to something. Okay, I want you to be able to predict that, knowing that H minus is going to be the base, because that is a strong negative charge on that hydrogen, and it would remove the acidic hydrogen on the carbon. Okay, and so that ends up giving us this carbanion on the right side, the products, as well as H2, which is elemental hydrogen. It's a gas. Okay, so now that we've got this set up, we want to kind of go over or give you the pKa's. So you should be able to look these pKa's up in a chart in the back of your books. There is an appendix. And the pKa of this ethylene is 44, while the pKa of hydrogen is 35. So remember, the lower the pKa, the stronger the acid. That means that pKa 44 being larger is the weaker acid. And so what that means is that the weakest acid and the base are favored. And so since we have the weakest acid on the left side, the reaction does not move forward and it favors the reactants. Okay? In other words, we cannot move forward and hold up. They can't do that. Sorry, I like Fresh Prince. And I saw this in the GIF option, so I thought I'd throw it in there. Might not even be super relevant, but I had to throw it in there because it's fun. But basically, that's why knowing the pKa values is really helpful, because it can tell you whether or not a reaction can move forward. And in that case, it wasn't really moving forward. The equilibrium was favoring the reactants, and sometimes it could be pretty much to the point where nothing at all is happening. So it's important to remember that pKa's are logarithmic, right? And so the difference between pKa of 1 and a pKa of 2 is not just one unit, or it is one unit, but it's not just one value that's like, it seems really small, right? But it's a value of 10. So it's logarithmic, And so that means that pKa 1 and pKa 3 is 100 times weaker than pKa of 1. Okay, so we've got this guy drawn out for you, and kind of just getting through. We got the acid, we got the base, and now we're attacking the proton, and the 2 electrons go to the oxygen to give us that carboxylate product on the right side, and ethanol as well. Now let's write the pKa's. pKa of acetic acid is about 4.8, while the pKa of ethanol is 16. So pKa of 16 is definitely higher than pKa of 4.8, which makes it weaker. And being the weaker acid, that means we are going to favor the products. And so sometimes when you favor the products in an equilibrium reaction, you can have a large arrow going to that side and then a smaller arrow going to the other side. And so that's why I've drawn in red is an equilibrium arrow that kind of has the larger arrow going towards the product side, because this equilibrium would favor the products. And that means that the reaction would proceed as desired. And so, all right. That means we are happy, so we do a happy dance. Alright, so if you've never seen Fresh Prince, shame on you, but also it's probably on like Nick at Night or Netflix or some other streaming device, and you should definitely check it out because it stands the test of time, and it's amazing. And most of my daily quotes, not most of my daily quotes, a lot of my daily quotes come from Fresh Prince. So anyway, back to science. Alright, so which base is strong enough to deprotonate acetonitrile? In parentheses, CH3CN. So the products are favored. Alright, so I'm going to write out a bunch of them, and then you got to do them on your own, of course, and then see if they match my answers. So NaH, that goes to H2, Na2CO3, that goes to HCO3 minus, NaOH goes to water, NaNH2 goes to NH3, and then NaHCO3 goes to H2CO3. So that's in order. That is sodium hydride, sodium carbonate, sodium hydroxide, sodium amide, and sodium bicarbonate. They go to H2 gas, bicarbonate, water, ammonia, and carbonic acid, having the pKa's of 35, 10.2, 15.7, 38, and 6.4. So let's do A first. The hydride plus acetonitrile goes to H2 and this conjugate base. Now, basically, write out the pKa's. pKa is 25 for acetonitrile, that's given. pKa of 35 for H2. That is the weaker acid, so this reaction will proceed. Yeah. Gotta do that Carlton dance. That was a... Alright, so CO3 2 minus. That's the, then we got CH3CN for our acetonitrile going to bicarbonate as well as our conjugate base. Alright, so based on the numbers I gave you above, we've got a pKa of 25 for acetonitrile, and then we've got a pKa of 10.2 for the bicarbonate. So since acetonitrile is the weaker acid, that means we are not moving forward, and there you go. Will Smith said it all. Cannot move forward. So let's try letter C, JK. Hydroxide plus acetonitrile goes to water and our conjugate base of acetonitrile. So you guys should get really familiar with the pKa's of a lot of these common ones, especially the list that I just gave you. And not necessarily saying you need to memorize them, but I feel like eventually you kind of just will because you use them so much. It is really helpful though. I'm not going to test you on like what's the pKa of water, right? So sorry, I'm just kind of writing these things out as we go because I'm hoping that you already did them and you got the same answer, right? So acetonitrile is a weaker acid than water, and so that reaction does not move forward. And then we've got pKa of 25 for this, and then pKa of 38 for ammonia. For this particular reaction, pKa of 38 is a weaker acid, and therefore this reaction will move forward. Yeah. Excuse me, hopefully that wasn't too loud. But we've got the bicarbonate plus acetonitrile again. That's going to carbonic acid. So, writing in this app, it always does weird shapes with whatever I'm drawing. So, sorry if that happens occasionally. It gets a little frustrating. But we've got our pKa of acetonitrile 25 and our pKa of carbonic acid 6.4. pKa of 25 being the weaker acid. Therefore, the reaction should not proceed forward. Now, one thing I want to point out is bicarbonate is something called amphiprotic, and that means it can either give up a proton or receive a proton. And we saw this because carbonate gained a proton to make this bicarbonate ion, but then bicarbonate ion can remove a proton to become carbonic acid, and so it acts as an acid as well as a base. Fancy stuff here. All right, so that's pretty much it for that one. So go ahead and get that practice in. All right.